Imagine absolute, impenetrable darkness, broken only by the cold glow of distant stars. You are at a distance of 384,400 kilometers from your home planet. Under your feet is the ancient dust of the lunar South Pole, and above your head is an infinite ocean of vacuum. The only thing that connects you with civilization, with family, with the billions of people who remain there on the blue sphere, is the barely perceptible hiss of static interference in the helmet headphones. This is the voice of the Mission Control Center in the city of Houston. And now imagine that this voice disappears. Suddenly, without warning, the commands of the operators are replaced by dead silence. You look at the indicators of the communication system of the Orion spacecraft, but you see only red triangles of errors. The Deep Space Network of the National Aeronautics and Space Administration, known as the DSN, no longer sees your signal. You are the first humans on the moon in the last 50 years, and you have just become the loneliest beings in the known universe. Today, we will dive into one of the most disturbing and at the same time scientifically grounded scenarios of modern cosmonautics. The Artemis program is not just the return of a human to the satellite of the Earth. It is preparation for a jump to Mars, the construction of the first space station in the orbit of the Moon called Gateway, and the creation of a permanent base on the surface. But all this super-complex architecture rests on one extremely fragile foundation, which is the reliability of communication. What will actually happen if the astronauts of the Artemis mission lose contact with the Earth? Do automated protocols exist that are capable of returning the ship home without human participation? How can solar activity or the mysterious anomalies of the shadow zones of the moon block radio waves? We will analyze the technical reports of the National Aeronautics and Space Administration in detail, investigate the physics of signal propagation in deep space, and find out why exactly the south pole of the moon is the most dangerous place for maintaining stable communication. This is not science fiction. These are real challenges that the best minds of humanity are currently working on, from the engineers of the European Space Agency to the developers of the SpaceX company. Prepare yourselves, for we are beginning the countdown to the moment when silence becomes the main enemy of space explorers. To truly comprehend the vulnerability of the future missions of the Artemis program, we must look back to that era when humanity first broke the chains of Earth gravity. The history of the exploration of the moon is not only a history of triumphant steps on the regolith, but also a history of desperate struggle for every bit of information that was transmitted through the space abyss. In the 60s and 70s of the 20th century, radio communication was the only thread of Ariadne that did not allow astronauts to dissolve into non-existence. Each of the 6 successful landings of the Apollo missions was accompanied by an inevitable and disturbing phenomenon, which in the documents of the National Aeronautics and Space Administration was designated by the abbreviation LOS, meaning loss of signal. This happened at the moment when the command module went behind the far side of the moon. The giant rocky mass of the satellite, having a diameter of 3,474 kilometers, became an insurmountable physical shield for radio waves. For approximately 48 minutes of each orbit around the moon, the crew remained in absolute radio silence. The Mission Control Center in the city of Houston could only wait, watching the static noise on the monitors, hoping that the physics of celestial mechanics would work precisely and the ship would appear again from behind the lunar horizon. The most emotional description of this experience was provided by Michael Collins, the pilot of the command module of the Apollo 11 mission. While Neil Armstrong and Buzz Aldrin worked in the Sea of Tranquility, Collins remained alone in orbit. In his memoirs, he noted that in the moments of being behind the moon, he felt such loneliness that no human had known since the times of Adam. This was not a fear of a technical error. It was a deep philosophical realization of detachment from the entire human species. Scientific reports of that era emphasized that despite the flawless operation of the antennas of the so-called S-band, the physical blocking of the signal could not be overcome by the technologies of that time. However, humanity felt the true horror of communication loss during the dramatic events of the Apollo 13 mission in April 1970. After the explosion of an oxygen tank, saving energy became a matter of survival. Astronauts James Lovell, John Swigert, and Fred Hayes were forced to turn off almost all onboard systems, including part of the communication equipment. Every transmission to Earth was a luxury. The Mission Control Center worked at the limit of its capabilities, trying to catch weak signals among the space noise. When the ship went behind the moon for a gravitational maneuver, the waiting time for the signal seemed like an eternity. Even experienced engineers of the National Aeronautics and Space Administration later admitted that every second of delay beyond the calculated time was perceived as a final sentence for the crew. This case proved that communication is not just a way of transmitting data. It is a critical life support system, no less important than oxygen or water. The Soviet Union, moving in parallel, faced another challenge, which was the problem of signal delay and remote control. The Lunokhod program, which became the first successful experience of using automated self-propelled vehicles on another celestial body, revealed the complexity of control in real time. The radio signal, moving at the speed of light, which is approximately 300,000 kilometers per second, covered the distance to the moon and back in 2 6/10 seconds. For operators on Earth, this meant that they saw the picture from the television cameras of the Lunokhod from the past, and their commands reached it with a delay. This created the effect of a drunk driver, where any error in maneuvering could lead to the fall of the apparatus into a crater even before a person has time to react. Today, preparing for the Artemis program, we rely on these lessons, but the scales of complexity have increased exponentially. If in the era of the Apollos, the loss of communication was a planned part of the orbital motion, then in modern missions, where the construction of a base on the South Pole is planned, any unpredictable silence can become fatal. The South Pole of the Moon is a land of eternal shadows and deep craters, where the direct line of sight of the Earth is often interrupted by the features of the relief. That is why scientists of the European Space Agency and the Japan Aerospace Exploration Agency are currently actively developing projects similar to the Moonlight program, which is intended to create a constellation of navigation satellites around the Moon. This is something that the pioneers of space did not have. An attempt to create a lunar internet that would guarantee that the phrase "we do not hear you" would never sound in the headphones of astronauts again. Analyzing historical data, we see a clear pattern. Every major accident or dangerous situation in space was accompanied by the degradation of communication channels. The failure of sensors on board the Skylab station, difficulties with the docking of Soyuz Apollo. Everywhere, the information vacuum intensified the risks. Now, when we plan to send the first woman and the first person of color to the surface of the moon, engineers are forced to consider even such phenomena as the influence of cosmic dust on antennas and the deformation of structures due to extreme temperature drops from -173 to +127 degrees Celsius. History teaches us that in space, silence is not gold. It is a threat. And to avoid repeating the dramatic moments of the past, we must understand the physical nature of how exactly a signal is born and how it dies in the void. In the next block, we will break down the technical basis of how the nervous system of the Artemis mission is arranged and why even the most advanced technologies of the 21st century may be powerless before the laws of physics. To understand how a critical failure can happen, we must first disassemble how the most complex communication system ever created by humanity works. If the Apollo missions relied on relatively simple radio channels, then the Artemis program is a true digital ecosystem deployed in deep space. Its foundation is the Deep Space Network, which in the National Aeronautics and Space Administration is called the DSN. This network consists of 3 giant ground complexes located approximately at an angle of 120 degrees to each other around the entire globe. In Goldstone, state of California, near Madrid in Spain, and near Canberra in Australia. Such strategic placement guarantees that when the Earth rotates, at least one station is always looking at the moon. Each station is equipped with antennas whose diameter reaches 70 meters. This is the size of a football field, directed at the sky for catching incredibly weak signals, the power of which is sometimes less than that of the battery of your wristwatch. The heart of the mission itself is the Orion spacecraft. On its board, a new generation communication system is installed that uses phased antenna arrays. Unlike old dishes that had to be physically turned toward the Earth, These antennas can direct the beam of electromagnetic waves electronically in fractions of a second. Orion uses two main types of waves: S-band for transmitting commands and telemetry, and also K-band, which allows transmitting high-definition video and large volumes of scientific data. But here lies the first vulnerability. The high frequencies of the Ka-band require extreme pointing accuracy. A deviation of only a few hundredths of a degree, and the communication disappears. However, the most important innovation of Artemis is the Gateway Lunar Station. Imagine it as a space router that constantly circles the satellite of the Earth. Gateway will move along a very specific trajectory, which scientists call a near rectilinear halo orbit, or NRHO. This orbit was chosen not by chance. It resembles an elongated ellipse that allows the station to be within the direct line of sight of the Earth most of the time, while flying extremely close to the south pole of the Moon. This is critically important, as it is on the South Pole in the Shackleton crater that the astronauts will work. Gateway will serve as a bridge. It will receive a signal from the astronauts on the surface and forward it to the giant DSN antennas on Earth. Scientific reports of the European Space Agency, which is developing the IHAB residential and communication module for the Gateway Station, emphasize that such an architecture aims to eliminate the same 45 minutes of silence that were the norm for the Apollos. Theoretically, communication should be continuous 24 hours a day. But this solid-looking construction has its weak points. It depends on the flawless synchronization of dozens of satellites, ground stations, and onboard computers. As leading experts in aerospace engineering explain, for example, professors from the Massachusetts Institute of Technology, any delay in processing the signal at the Gateway Station or a failure in the software of the navigation systems can lead to a domino effect. If the station loses orientation in space for even a few minutes, its antennas will turn away from the Earth, and the entire nervous system of the mission will be instantly paralyzed. Moreover, we must consider the so-called link budget, which is the calculation of how much signal energy is lost while overcoming thousands of kilometers of vacuum. Every connection, every transition from the surface of the Moon to the Gateway and further to the Earth is a point of potential break. Reports of the National Aeronautics and Space Administration for 2024 note that even cosmic dust raised by the engines of the Ascent module can create short-term interference for microwave radiation. Thus, we have an incredibly complex network that unites the Earth, the orbit of the Moon, and its surface. This is a triumph of engineering thought, but at the same time, it is a trap. The more complex a system is, the more elements it contains that can fail. And at this moment, we move to the main question. What forces of nature are capable of breaking these technological chains? What can be stronger than 70-meter antennas in modern computers? We have built giant antennas, launched super-complex repeaters into orbit, and taught computers to exchange data in fractions of a second. But in space, we will never be masters of the situation. Our technological power is only a thin film on the surface of a turbulent ocean of physical phenomena, each of which is capable of turning the most modern communication channel into useless noise. The first and most powerful enemy of any space communication is our own sun. Although the sun gives us light and life, for the engineers of the National Aeronautics and Space Administration, it is primarily a giant source of electromagnetic chaos. Every 11 years, our star passes through a cycle of high activity. During this period, so-called coronal mass ejections occur on its surface. Colossal clouds of charged particles racing through space at speeds of millions of kilometers per hour. When such a flow reaches the Earth-Moon system, it causes geomagnetic storms. For the Artemis astronauts, this means not only a threat of radiation exposure, but also a complete blackout. The charged particles of the sun create an incredible level of radio interference, which literally jams the useful signal from the Orion ship. Scientific reports of the Goddard Space Flight Center state that during extreme solar flares, the power of background noise can exceed the power of the transmitter signal by dozens of times. This is like trying to hear the whisper of a child in the middle of a runway where the engines of a jet aircraft are working. The second fundamental obstacle lies in the geometry of the lunar landscape itself. The Artemis program is aimed at the south pole of the Moon, a region where the sun never rises high above the horizon. Here, deep shadows and giant craters reign, the walls of which reach several kilometers in height. For radio waves, which behave in many ways similarly to visible light, these walls are impenetrable barriers. If an astronaut on a lunar rover drives behind the edge of a deep crater, for example, such as Shackleton, he falls into the zone of the so-called radio shadow. Science calls this phenomenon diffraction at a sharp edge. Radio waves can bend slightly around an obstacle, but at the same time, their energy falls rapidly. Research published in the journal Nature emphasizes that at high frequencies, which Artemis uses for video transmission, this effect becomes critical. Even a small hill between the astronaut and the repeater can instantly cut off communication. That is why the engineers of the European Space Agency insist so much on deploying a network of miniature satellites in low lunar orbit that could look into these dead zones. Besides the relief, there is another less obvious but extremely treacherous threat, which is lunar dust, or regolith. This is not just ordinary dust to which we are accustomed on Earth. Due to the constant bombardment by micrometeoroids and solar wind, the particles of regolith on the Moon are extremely sharp and have a static charge. During the operation of the engines of the landing module, or even during the movement of the lunar rover, these particles rise up, creating a cloud of electrically charged suspension. Scientific experiments conducted as early as during the Apollo missions showed that such dust can lead to a triboelectric discharge. Imagine constant static sparks appearing around the antennas. This creates wideband interference that introduces digital errors into the data packets. One wrong bit in a command line, and the Orion computer may reject an important maneuver as erroneous. We must also not forget about the fundamental law of physics, which is the inverse square law. While the signal covers 384,400 kilometers, its energy dissipates in a huge volume of space. Every kilometer of vacuum is a loss of power. To catch this barely living signal, the DSN ground stations use cryogenic cooling of their receivers almost to absolute zero, which is minus 271 degrees Celsius. This is done so that the thermal motion of atoms in the antenna itself does not drown out the voice from space. Any slight increase in temperature in the receiving equipment on Earth and communication with the Moon will be lost just as effectively as if we simply turned off the power. We see that space is not just emptiness. It is an aggressive environment where every photon leads a struggle for survival. From solar storms to microscopic dust, nature has thousands of ways to make us silent. And when these physical factors overlap, a situation arises for which it is impossible to fully prepare by any training. We have considered the forces of nature, but what happens if the enemy is hiding inside the system itself? In a world where every millimeter of a spacecraft is controlled by complex software, a technical failure or even a deliberate intervention can become those fatal factors that will break communication forever. The Artemis program is the pinnacle of engineering, but at the same time, it is millions of lines of code, thousands of sensors, and hundreds of mechanical drives, each of which has its own endurance limit. The first scenario that security specialists of the National Aeronautics and Space Administration are considering is physical damage to the antenna system. The Orion ship and the Gateway station are constantly under the fire of micrometeoroids. These tiny particles of space dust, moving at speeds of up to 30 or even 40,000 kilometers per hour, have the kinetic energy of a bullet. A report for 2023 on the risk assessment for the Artemis II mission indicates that even a grain of sand 2 millimeters in size can disable the pointing mechanism of a phased antenna array. Without the ability to precisely direct the beam to the Earth, Orion will go silent, although all its other systems will work perfectly. This will create a situation of a silent observer. The crew will see the Earth but will not be able to say a single word to it. The second, significantly more modern challenge is cybersecurity. In the 21st century, space has become part of the global information space. Specialists from the Jet Propulsion Laboratory warn of the possibility of so-called spoofing or signal replacement. Theoretically, attackers or hostile state structures may try to send false commands to the board of the Gateway station that imitate signals from Houston. If encryption protocols are compromised, The ship may receive an order to turn off the main transmitters or reorient the antennas into the void. This is a new type of piracy where the weapon is not cannons but algorithms. Research published in the journal Space Policy emphasizes that protecting the communication channels of the Artemis program requires quantum-resistant encryption, because the usual signal delay of 2.5 seconds makes the immediate detection of a hack an extremely difficult task. The third scenario is metal fatigue and radiation degradation of electronics. Outside the protective magnetic field of the Earth, cosmic rays constantly attack the semiconductors of onboard computers. Individual heavy ions can cause so-called single-event upsets, changing the values of bits in the memory of the communication system. If such a failure occurs in a critical module responsible for decoding DSN signals, the crew will receive only a meaningless set of characters. Engineers of the SpaceX company and Lockheed Martin use triple redundancy where 3 computers perform the same operation, and if one is wrong, the other 2 correct it. But what if a powerful radiation flare disables all 3 modules simultaneously? In the history of cosmonautics, there have already been cases when, due to a static discharge, computers entered an infinite loop of rebooting, leaving the ship defenseless. Also, we cannot ignore the human factor on Earth. The deep space network is a complex ground infrastructure. A flood, an earthquake, or even a large-scale power accident in California or Australia can disable one of the 3 key supporting points. Although the National Aeronautics and Space Administration has backup plans for picking up the signal with other antennas, the complete loss of one of the ground stations at a critical moment of landing on the Moon will lead to chaos in the coordination of actions. Thus, a catastrophic failure of communication is not necessarily one major accident. It can be a chain of small events. A micrometeoroid damages a cable, radiation causes an error in the code, and the signal delay prevents operators on Earth from sending a patch for correction in time. At this moment, the astronauts remain alone with the void. Their fate no longer depends on the prompts of scientists. It depends on their own will and the ability to maintain calm in the most terrible silence in human history. When the radio airwaves go silent and the inscription "No signal" appears on the monitor screens, technical problems recede into the background. A real test begins that cannot be calculated on supercomputers, the test of the human psyche. At a distance of 384,400 kilometers from home, silence ceases to be just an absence of sound. It turns into a physical weight that presses on the consciousness of every crew member of the Artemis mission. In the psychology of aviation and cosmonautics, there is a term called the break-off phenomenon. It was first described in the middle of the 20th century by pilots of jet aircraft who rose to extreme altitudes. This is a feeling of complete detachment from the Earth, when the planet seems like something distant, alien, and unreal. For the Artemis astronauts who have lost communication, this effect is amplified thousands of times. Scientific works of the Behavioral Health and Performance Department of the National Aeronautics and Space Administration note that sudden isolation can lead to disorientation and cognitive distortion. A person begins to perceive themselves not as part of a large team, but as a lonely being thrown into a hostile ocean of vacuum. A special responsibility at such a moment falls on the shoulders of the spacecraft commander. In ordinary conditions, every decision, from changing the course to choosing the ration, is discussed with hundreds of experts in the Mission Control Center in Houston. But when the connection is broken, democracy in space ends. A time of absolute autonomy comes. The commander must take upon themselves the burden of sole responsibility for the lives of 3 other people. Is it worth continuing the implementation of the scientific program if the connection has disappeared? Is it necessary to immediately launch the engines for an emergency return, risking fuel that might not be enough for a complex maneuver? Research conducted during long isolation experiments, such as Mars 500 or stays at stations in Antarctica, shows that in conditions of stress, the human brain is prone to tunnel thinking. This is a state where a person focuses on one, often secondary problem, ignoring the overall picture of the threat. Without external control from the Earth, which usually acts as a collective mind, the crew may make a critical error in calculations simply due to fatigue or psychological pressure. specialists of the European Space Agency are developing special protocols of silent interaction. This is a set of pre-written algorithms that astronauts must perform mechanically without wasting time on arguments. Every second of reflection in space is lost kilometers of trajectory. For example, if communication is not restored within 72 minutes, this is an automatic signal to prepare for undocking from the gateway station. But there is also another aspect, which is the ethics of choice. Imagine that during the stay on the surface of the Moon, one of the astronauts receives an injury, and the connection with Earth is absent. The commander cannot receive a consultation from the best surgeons in the world, who usually are on duty on the communication line. He must decide for himself to perform a dangerous medical manipulation in conditions of low gravity, or to evacuate urgently, which may mean the failure of a mission worth billions of dollars. The psychological resilience of Artemis astronauts is trained for years. They are taught meditation techniques, methods of fast decision-making, and ways of stopping panic attacks. However, no training in a pool or a preparation center can fully imitate the moment when you look at the blue point of the Earth in the porthole and realize that it no longer hears you. This is a moment of highest existential tension where science meets the philosophy of survival. We must understand that the success of the mission depends not only on the strength of the titanium hull of Orion, but also on the strength of the nervous system of the 4 people inside. In the next section, we will consider what technological lifebuoys engineers are creating to help people overcome this information vacuum and return home even when the radio airwaves fall silent forever. When traditional radio channels are silent and the deep space network does not see a signal, technologies that seemed like pure science fiction only 10 years ago come to the rescue. Scientists of the National Aeronautics and Space Administration and engineers of private companies understand that to make humanity a truly interplanetary species, we must teach our ships to think independently and communicate in new, more advanced ways. The first revolutionary technology that is already undergoing testing within the Artemis program is optical or laser communication. During the Artemis II mission, a system called the Orion Optical Terminal will be tested for the first time. Unlike radio waves, laser beams have a significantly higher frequency, which allows transmitting data at a speed of up to 260 megabits per second. This is dozens of times faster than the best K-band radio channels. But the main advantage of the laser is not only in speed. The laser beam is extremely narrow and concentrated. This means that it is much harder to jam it with solar interference or intercept it. However, the narrowness of the beam is also the main challenge. To transmit a signal from a distance of almost 400,000 kilometers, the pointing system must have an accuracy equivalent to hitting a 5-cent coin with a laser pointer from a distance of 10 kilometers. Scientific reports of the Jet Propulsion Laboratory confirm that if this technology becomes standard, even in the event of failure of the main antennas, astronauts will be able to use a backup laser channel for transmitting telemetry and video communication. And what if the ship completely loses orientation and does not know where to direct its antenna or laser? Here, artificial intelligence and autonomous navigation enter the game. Modern spacecraft are increasingly equipped with systems for navigation by X-ray pulsars. Pulsars are neutron stars that rotate at enormous speeds and emit strictly periodic pulses of radiation. They are natural cosmic beacons. Using X-ray sensors, the onboard computer of Orion can measure the arrival time of pulses from several pulsars simultaneously. Comparing these data with a knowledge base, artificial intelligence is capable of calculating the coordinates of the ship with an accuracy of up to several kilometers without any help from ground DSN stations. This is effectively a cosmic analog of the global positioning system that works at any point in the solar system. Research published in the journal Science proves that the sextant experiment conducted on the International Space Station confirmed the viability of this idea. For the Artemis astronauts, this means that even in complete silence, the ship will always know the way home. The third echelon of protection is the creation of a lunar infrastructure independent of Earth. The European Space Agency is actively working on the Moonlight program. This is a constellation of satellites that will constantly orbit the Moon, creating a stable network of coverage even over its far side and in the deep craters of the South Pole. If direct communication with Earth is interrupted, Moonlight will automatically intercept the signal and will store it until a window of visibility appears with one of the ground stations. This brings us closer to the concept of a lunar internet, a protocol for delay-tolerant networking where data is transmitted in parts without being lost when the connection breaks. We see that the future of space exploration is a transition from the model of remote control to the model of an autonomous mind. We teach technology to be independent so that a human never remains truly lonely. However, despite all the lasers, pulsars, and artificial intelligence algorithms, one question remains to which science has no answer yet. How will we change as a species when we realize that our connection with our home planet is only a thin thread that can be broken at any moment by the majesty of the universe? We have come a long way from the first radio signals of the Apollo era to the super-modern laser systems of the Artemis program. We have disassembled the physics of solar storms, the treachery of lunar dust, and the fragility of the human psyche in conditions of absolute isolation. Now the time has come to provide an answer to the main question. Is the loss of communication in space the end of the mission? Or is it just a new, most severe stage of testing our civilization? The loss of contact with the Artemis crew at a distance of 384,400 kilometers is not just a technical failure. It is a moment of truth for all of humanity. The Artemis program is the foundation for the future jump to Mars. If on the Moon, the signal delay is only 1 3/10 of a second one way, then on the way to the red planet, it will reach 20 minutes. This means that any expedition to Mars will by default be in a state of loss of communication from the perspective of operational response. The Moon is our training ground where we learn to be autonomous, to make decisions without prompts from Earth, and to trust artificial intelligence algorithms just as we trust oxygen tanks. The scientific community, in particular leading astrophysicists and engineers of the National Aeronautics and Space Administration and the European Space Agency, are convinced that silence in the airwaves is not a defeat. It is a transition to a new level of evolution of the explorer. When the Orion spacecraft disappears from the radars of the Deep Space Network, it does not cease to exist. Inside it, the hearts of 4 brave individuals who have passed thousands of hours of training continue to beat. In its memory, the experience of millennia of star observations is stored. Even if the antennas are silent, the laws of Kepler and Newton continue to act, directing the ship along the invisible rails of celestial mechanics back to the home planet. Philosophically speaking, we must realize that our connection with the Earth is not only radio waves. It is the knowledge that we take with us. These are the protocols we have developed and the values we protect. Space silence makes us think about how small we are on the scale of the universe, but at the same time, how great we are in our desire to understand this universe. Every failure in the communication system is a lesson that makes the next mission safer. Every minute of uncertainty is the price we pay for the right to call ourselves an interplanetary species. Summarizing our deep dive, it can be said with confidence. Yes, loss of contact with Artemis astronauts is one of the most likely and dangerous scenarios. However, we are prepared for it better than ever in history. We have laser beams piercing the vacuum, artificial intelligence that navigates by pulsars, and, most importantly, we have the will of people who know that even in the darkest and most silent abyss, they are not alone as long as science leads them. We conclude this story, but space exploration continues every second. In your opinion, should humanity rely completely on automated rescue systems, or should the last word always remain with the person on board, even if they are cut off from the whole world? Could you withstand 48 minutes of complete silence, knowing that behind the porthole there is only infinite blackness? Share your thoughts and theories in the comments. Subscribe to the channel so as not to miss new analyses of the most complex riddles of space. Remember, even when the signal disappears, the search for truth never stops.